Sure. All right, good afternoon, everyone. My name is Rob Marquez, and I represent Guardian Technologies. We're here to present on the Biological Integrated Independent Biofeedback System, also known as BIBS. Our sponsor is Cubic Corporation and Kevin Priest. Next slide. This is our agenda for today. It's our introduction, our overview, final report, conclusion, and questions at the end. Next slide. Our mission is to develop a system to monitor vital signs in real time and transmit it to a command station. Now, what does that mean? Why are we doing this? Well, soldiers on the battlefield, firefighters in burning buildings, policemen in cities, they risk their lives to protect our lives. So what can we do to save their lives when they're in danger? Well, we can minimize and prevent casualties in dangerous environments. So we can monitor their vital signs just in case they're in danger or when they're in the critical state. Next slide. Now let me introduce my engineering team. I'm part of the integration team, myself, Rob Marquez, and Jamie Madrigal. Sensor team, Christine Gutierrez, Marco Lechuga, John Lavella Jr., and Jose Pintor. Next slide. Our PCB prototyping team, Jesse Bowman, Marco Ontiveros. Our software network team, Shivash Balakar, LJ Jamato, Sho Kikugawa, and Edwin Sandoval. Next slide. Now I'm going to pass it over to Edwin, who will be talking about the project plan.
So our project was divided into two parts, the Smart Vest and the command station. Our main part of our project is the Smart Vest, which has all the vital measuring sensors on the vest itself that monitors all our vital signs and transmits it back to our command station. All these sensors were with COTS products. COTS, if none of you know, it's commercial off-the-shelf products. When this data is received from each sensor, sent it to our command station, which has a GUI run in it and shows the real-time vital signs. If any critical state is reached, our GUI will alert the operator either with yellow or red, indicating the danger that that user or vest wearer is in. So this is our functional block diagram. The microcontroller is the main part of our vest. It has all our sensors, accelerometer, respiratory sensor, pulse oximeter, and thermistor. When data is gathered in the microcontroller, it packetizes it and sends it through our transceiver wirelessly to our command station. From here, like I said, the transceiver translates this data and it updates the GUI every second. As far as the transceiver or vest and command station is concerned, this wireless link is just serial communication. Now I'll pass it out to Robert.
Thank you, Edson. Now we're going to talk about sensor placement. In order to get the maximum and efficient sensor data, we're going to have to place it in places where kinesiologists, doctors have researched over the decade. Now, with the thermistor, we're going to place it under armpit. It's going to give us the perfect skin temperature. With the respirator stretch sensor, we're going to place it on the upper chest. It's going to give us displacement on inhalation and exhalation. For the pulse oximeter, we're going to place it on anywhere near the body, but we're going to place it near the heart so it can give us a better heart rate reading. Now, the wires and the cords are going to be placed down the side in order to be non-obtrusive to the wearer. Next slide. Here's the accelerometer PCB radio module. We're going to place it to the side. So it's behind your body and then there's a module on the side. Now with the battery, we're going to place it on the other side to prevent from any noise and for easy recharge. Next slide. I'm going to pass it on to Jose who will be talking about the thermistor sensor.
Okay, in order to approximate the body temperature, we're going to be using a biomedical NTC thermistor. NTC means a negative temperature coefficient. That means as the temperature increases, the resistance will decrease. This thermistor can measure temperatures from 0 to up to 70 degrees Celsius, which is about 30 to 160 Fahrenheit. But since body temperature only ranges from 95 to 102, we're just going to measure a little bit below and above that, which is like from 90 to 105 in increments of 0.2 degrees Fahrenheit. And let's say a person has a temperature of 97 degrees Fahrenheit, and the temperature suddenly increases. The next reading that the thermistor is going to give us is going to be 97.2, 97.4 until it reaches the actual body temperature. The reason why we picked this thermistor is because it gives us a fast, accurate, and stable temperature. The maximum error that we can get with this thermistor is about 0.45 degrees Fahrenheit. Now, Christine will talk about the accelerometer.
The model we chose is a free-scale accelerometer. It will measure, it will determine the position of the user, whether the person is lying down or standing up, from its triple axis, which is the X, Y, and Z axis. So the X axis will actually tell us if that person's lying down, and Z axis will tell us if that person is laying down, X axis if they're standing up. is MEMS device. MEMS device is a microelectromechanical system. It's a little machine that will determine what position that person is in. And it also has external resistive and capacitive filters for smooth output signal into the microcontroller. Up next is
Thank you, Cece. The respiratory rate sensor measures the breathing rate of the person who wears the vest. The breathing rate is the number of cycles of inhales and exhales per minute. The sensor that we used, it was a stretch sensor. The stretch sensor is shown here in the picture. It has electrical hook terminals at the ends of the sensor, so we can connect it to the circuit. And the sensor is stretch and relax as the chest motion is expands and contracts due to the breathing rate, to the breathing motion. The circuitry that we used to condition this signal was a Wheatstone bridge, an amplifier, and a low-pass filter. Next slide, please. So this is a plot that shows the peaks of the signal, show the exhales of the person, and the valleys of the signal show the inhales of the person. And here you can see this is a deep breath. Next slide, please. The first plot showed the person in rest, and this is the noise produced when the person is running. Now John will talk about the pulse oximeter.
Okay, so the pulse oximeter will be measuring two vital signs at once for us. The first one is heart rate, the second one is blood oxygen saturation. Blood oxygen saturation is the percentage of oxygen in your bloodstream. So the pulse oximeter has two parts. The first one is a reflectance sensor, the second one is a processing module. The reflectance sensor has two sets of LEDs and photodetectors. So when light is emitted onto the skin, some of that light is absorbed and some of it is reflected. The photodetector senses that light, sends it to the processing unit. That unit calculates a ratio and it gives us a percentage in terms of blood oxygen saturation. Now this reflectance sensor needs to be in contact with the skin at all times to maintain its accuracy. Next slide, please. Now in order for us to determine what all of the data from our sensors means, we needed to do extensive research. We went to hospitals, we spoke with emergency room doctors, kinesiologists, so that we could obtain minimum and maximum values for all of our vital signs. Now on the screen is a scenario where we have a 27-year-old male with specific demographics. Let's say he's a firefighter and he's wearing our vest. The algorithm in the microcontroller will take all the data from each sensor and it will determine the health state of our vest wearer. Now let's say we take a look at the first row. You're probably thinking, well, 175 beats per minute. Well, that's a little high, right? Well, what we had to take into account is that our vest wearer can be at rest and can be during movement, during exercise. So our algorithm will compensate for that. If somebody is exercising or if they're at rest, if they're anxious, this means that you'll have to compensate for that elevated vital sign. And of course, the vital sign states can be normal, abnormal, critical, irregular, depending on what the sensors are telling us.
Printed circuit boards. For the printed circuit boards, we divided them into sort of like two different systems. One board, which is a main board that goes on the back of the wearer, which provides all the power, has a battery connected to it. It's encased. It has the radio on it. It has the microcontroller on it. We put all the voltage regulation. Everything is on that single board. And then we have smaller individual boards that interface these sensors with the microcontroller. Those are mostly just analog boards with buffers and amplifiers and comparators. We have one for the respiratory rate sensor, one for the